Hello, my name is Rob Waller with Protect Heritage. This is one in a series of videos on the Cultural Property Risk Analysis Model, or CPRAM. This video will be about calculation of the total magnitude of risk. Can we add magnitudes of risk to arrive at a measurement of total risk? The answer is yes, but with caveats and with care. We must be aware of caveats because the total magnitude of risk can only be a gross approximation due to model uncertainties, including not all risks might be identified, not all cultural property values might be identified, and not all interdependencies between risks and risk factors are dealt with, and variable uncertainties, including imprecise mapping of concepts to numbers, variability within the cultural property, that is variability in susceptibility, values, and so on, and irreducible random variability. Still, estimation of total MR by summation of generic risk MRs does afford an opportunity to judge the overall reasonableness of a result. For example, estimating the risk of 0.5 or 50% loss in value over the next 100 years for Stonehenge would seem unreasonably high. In contrast, estimating the magnitude of risk of just 1 part per thousand over 100 years for a lending library collection would seem unreasonably low. Either of these results would encourage us to look very critically at our analysis for blatant errors, and so we can estimate the total magnitude of risk by calculating the sum of the generic risks. We must, however, correct for double counting of objects that might be destroyed or lost due to more than one risk. Let's consider this simple collection of 25 objects. Consider the possibility of flood, where we might expect 10 objects to be destroyed by the action of flood over the next 100 years. We might also expect 10 objects to be destroyed by the action of fire over the next 100 years. Now, a simple addition of those two risks would lead us to expect 10 plus 10, or 20 objects to be destroyed. But can this be right? Here we see that there are 4 objects that are expected to be lost to flood and again lost to fire. We need to subtract out these 4 counted objects, each of which could only be destroyed once. This leads us to expect to have 10 plus 10 minus 4 equals 16 objects destroyed. We need to subtract out the intersection. In general, when we are dealing with many risks, we need an overall mathematical solution to this issue. Consider the whole area of this rectangle to represent all the objects in the collection. This reddish circle represents the number of objects we expect to be lost due to fire over the next 100 years. This blue circle represents those objects we expect to be lost due to flood, and the yellow circle represents the number of objects we expect to be lost due to theft. Now, this area outlined in green represents the pairwise intersection of fire and flood loss. If we simply add fire and flood risk, we would be double counting the loss of these objects. Similarly, we can identify the pairwise intersections of fire and theft and of flood and theft. Simply adding these 3 risks together would result in double counting of all of these areas of intersection, so they would need to be subtracted from our result, as we see here. If we do that, we can see that this central area, here outlined in blue, would have been added to our result 3 times, once for each of the 3 risks, and then subtracted out 3 times, once for each of the pairwise combinations of risk. We need to add back this 3-wise intersection 1 time in order to get the proper answer for our total risk. In theory, we would need to subtract out any any 4-wise intersections of risk, then add back any 5-wise intersections of risk, subtract out 6-wise, add back 7-wise, and so on. In practice, these corrections become negligibly small, even after just 3-wise intersections, and further corrections can be ignored. These corrections are done assuming independence of action of the risks considered. We should be aware, however, that they are not always independent. Let's look at how extreme our errors might be if we incorrectly apply that assumption. Here, let us consider that the 10 objects we expect to be destroyed by flood happen to be the same as the 10 objects we expect to be destroyed by fire. Perhaps those 10 objects are stored in a poorer part of the building or in an outbuilding. In this case, we would expect the total risk to not be 10 plus 10 minus 4 objects, but rather the 10 objects we expect to lose due to flood, plus the 10 objects we expect to lose due to fire, minus the 10 objects in the intersection. So our total is just 10 objects instead of 16. In the other extreme, we might consider expecting to lose 10 objects due to flood, and then to lose a separate 10 objects due to fire. Here, the two parts are completely separate. We expect completely different objects to be lost to flood from those we expect to be lost to fire. Perhaps the fire risk objects are stored in the attic, while the flood risk objects are stored in the basement. In this case, calculation of the total risk should be 10 objects due to be lost to flood, plus 10 objects we expect to be lost to fire, minus no objects in the intersection, to give a total of 20 objects, instead of 16 in the case where we assume independence. In practice, our assumption of independence of risk has proven adequate for the summation of magnitudes of generic risks, at least in terms of getting a sense of how much of the collection we do expect to be lost over 100 years.